Hi everyone, and welcome to another lesson on motion. I'm actually going to proceed in this video with the assumption that we haven't yet covered the motion formulae, which are v equals u plus at, s equals ut plus half at squared, v squared equals u squared plus 2as, and s equals u plus v bracket times t over 2. If you haven't seen those before, that wouldn't have made much sense, but if you have seen them before, then you definitely know what I'm talking about. I'm going to do this video with the assumption we haven't covered them yet. And the main thing I want to show you in this video is that the secret to solving questions that have a lot of information or are, I guess, conceptually tricky in some way is to draw. Draw pictures, draw graphs, draw shapes, draw lines, draw triangles, circles, lots of arrows, and label everything. Even if you don't get the question right, that's still evidence of working. So with that being said, let's launch into the first question I'm going to put for you. And it's a question I think that benefits from having drawn a few graphs. There's a toy car pictured here, traveling at time, we'll say t equals 10 seconds, at 25 meters per second to the right there. And I'm not going to include arrows for velocity because we'll just say that that is the positive direction of velocity. So if I say the initial velocity, we'll say u, is equal to 25 meters per second, you automatically know it's moving that way. If this value were negative, it would be moving in the opposite direction. So it's starting to move at 25 meters per second at time t equals 10 seconds. And then it hits this tract of mud here. And it slows down to a stop. So the final velocity is 0 meters per second. And the time taken for it to slow down is 2 seconds. This would be at t equals 12 seconds. So 2 seconds later, it's lost all of that velocity that it had. The question I'm going to ask is, what was the acceleration of this toy car? Now, if you were to calculate acceleration using the formula acceleration equals v take u on t, we could solve this question very quickly. That would be 0 take away 25 on delta t, so the change in time from 10 to 12, that's 2 seconds, or negative 12.5 meters per second squared. But what I want to do is draw the graph of velocity and find the acceleration from there. So that's velocity on the vertical, time on the horizontal. The key times we're dealing with are 10 seconds and 12 seconds. And the key velocities we're dealing with are 25 meters per second and 0 meters per second. So we'll say for the first 10 seconds it was at a constant velocity. That means we have a straight line here. It also says to us the gradient of that line is 0, therefore the acceleration in those first 10 seconds was 0. But in this 2 seconds here that has elapsed between these two pictures, it decelerates, or it has negative acceleration. So it goes from 25 meters per second to 0. So at t equals 12, we can mark that point in there. And then if we assume it has constant acceleration, we just draw a straight line down, linking those 2 points there. The gradient of a velocity time graph is the acceleration. So let's work out the gradient here. Well, first of all, it has a run of 2 there, and it has a rise of negative 25. So the gradient is equal to negative 25 on 2, or negative 12.5 meters per second squared, because that's negative 25 meters per second, and that's 2 seconds. So meters per second divided by seconds is meters per second, or meters per second squared. So we get the same result whether we look at this formula here or the graph. The benefit of using the graph is that we could also figure out, without using a motion formula, the amount of stopping distance it took to stop this car. So that would be from the front of the car there to the front of the car there, assuming it starts stopping at that instant there. And the stopping distance will be given by the area under the velocity time graph in that region there. The area under an acceleration graph, this is acceleration over time, is the change in velocity. The area under a velocity time graph is the change in displacement. So let's figure out the stopping distance now. The stopping distance being the area here. Well, the area of a triangle is base times height over 2, which here is equal to 2 times, we'll say 25 divided by 2, which comes to 25 meters. So it took 25 meters for this toy car to stop, but it only took 2 seconds. Moving on to the next question I want to look at. This question benefits more so from using the graph than the formulae. So deleting all this, we'll just give this one in text form. So a car accelerates from rest. A car accelerates from rest. Acceleration is equal to 1/2 meters per second squared. And it does this for 4 seconds. Then the acceleration is equal to -2 meters per second squared for 2 seconds. And the question we want to ask is, what is the displacement at 6 seconds? The key to solving this question here is to draw the velocity time graph. So velocity here and time here. The car accelerates from rest. So at t equals 0, the velocity is also 0, so we can mark a point in there. It then accelerates at 1/2 meter per second squared for 4 seconds. And that indicates to us that every second the velocity increases by 1/2. So if we have 1 second, 2 second, 3 second, 4 second, 5 seconds, 6 seconds, after the first second, the velocity, 1, 2, 3, 4, the velocity is at 1/2 meters per second. So meters per second and seconds. So we'll say that's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. After 2 seconds, the velocity is risen by another 1/2 meter per second. After 3 seconds, it's half again. And after 4 seconds, the velocity is 2 meters per second. And that's when it finishes that first acceleration. Then the acceleration is -2 meters per second squared for 2 seconds. So that says for every second that passes, the velocity drops by 2 meters per second. So after this one more second, between 4 seconds and 5 seconds, we expect the velocity to drop from 2 meters a second to 0. And then I forgot to put the negative part of this graph in here. -1, -2. But after another second, between 5 and 6, we expect the velocity to be all the way down here at -2 meters per second. So if we join up all those points, velocity reaches a maximum, velocity returns to 0, and then becomes negative. That tells us that the car starts at rest. It then accelerates very quickly to a maximum, slows down, and then down here, it's indicated that the car will turn around. So at t equals 5 seconds, it'll reach its maximum distance from the origin. Let's figure out the displacement. We said the area under a velocity time graph is equal to the displacement. So what we're going to do is find the area under here, and then we have what we can think of as a negative area under there. So it's the red area being taken away from the blue area. the area of this triangle here, or the area of a triangle, is base times height over 2, which is equal to, well, the base is 5 seconds, the height there is equal to 2 meters per second, and divide that by 2, I get a total of 5 meters. So we said the car started from rest, accelerated, slowed down, and then turned around. Right before it turned around, it reached the 5 meter mark there. And then it actually lost some of its displacement. It started to return here towards the origin. So the area under this section here, the red area, is equal to base times height over 2. That comes to 1 times the height is, well, it's negative 2, divided by 2. That's negative 1 meter. So it's a bit odd thinking in terms of negative area, but just remember it did have a negative height. So we have a negative area there. So I said we should take away the red area from the blue area, but since we are working with a negative area here, we can actually add them together. So the area 1 plus the area 2 is equal to 5 meters plus negative 1, otherwise known as taking away 1, which is equal to 4 meters, which is the final displacement of a car that follows these acceleration patterns here.